Welcome everybody, also from our side, from Switzerland. Maybe to begin with, to those of you that don't know us, a few words about vario-optics. We're located in Switzerland. We are a spin-off from Varioprint. Varioprint is a PCB manufacturer. This will be important later on in my presentation, because what we're doing is really what we call Electro-Optic Circuit Boards. And this is really my goal for today, to explain what we are doing, what is an Electro-Optic Circuit Board, why are we doing and developing those, and how can you develop those and use them. Luckily, we had really interesting talks already, so I can go through this introduction very fast. I think we're all on the same page that PICs, various technologies, various materials and platforms exist, and they can be used in a growing amount of applications, not only in communication, but also sensing or even quantum computing. So this is a very exciting field. And what we've also heard in the previous talks is that it's not only about the PIC platform itself, so about the photonic chips, but also very much about the surrounding infrastructure. So how can you test those PICs? How can you package them, integrate them into a complete system and product? And this is, of course, clear that a PIC is not a standalone system. Quite often you need some electrical driving chip, some standard IC. You need maybe an RF interface. We've already heard there might be some thermal issues. So connecting a PIC is not a trivial thing. It's much more, I would say, multidisciplinary task, which personally I think is really the beauty of it. It's a very interesting field. But on the other hand, this is also part of the reason why it is so hard and still challenging to make a good package to a PIC. And this is exactly the niche or the gap where vario-optics is active in. What we do, these electro-optic circuit boards, looks pretty much like a standard circuit board, printed circuit board for electrical components. And the idea is to expand this concept of an electrical circuit board with optics. So the idea really is that you can take those PICs, you can also take the electrical ICs, you can mount all of them onto such a board, and you get access both electrically and optically. So this is really the takeaway message from my presentation. So let's have a deeper look into this. As mentioned, these PCBs that you see here really looks like an electrical one. So there is actually an RF interface up to 70 gigahertz on this board. And while you don't see it, there is actually also an optical layer on top. And this is very similar to what Sander mentioned in his previous talk. So this is an optical layer made of polymer material, which consists of planar waveguides. And those waveguides can be used to basically serve as a fan out from either a chip to a fiber interface. But you could also, for example, connect different photonic chips on such a substrate. There, of course, a very important part are optical interfaces. So I will show you later on 2 examples of how you can couple a silicon photonics chip, for example, or indium phosphide chip to these waveguides. And as mentioned, of course, it's also very important that we can rely on all the standard and advanced PCB manufacturing technology. This is why it's still important for us as vario-optics to be very closely working together with Varioprint on these boards. Right, so talking about these planar waveguides, as mentioned, the material we're using here is a polymer. That means it's a liquid polymer that we spin onto the substrate or on different substrates. It cures under UV light. That means we use photolithographic tools, different mask-based tools to structure these cores of the waveguide. So it's a 3-layer process. There's a lower cladding, there are the cores of the waveguides, and there's an upper cladding. So you can also imagine in terms of cost and effort, such an optical layer is more or less 3 times that of an electrical layer in a standard PCB. We typically structure those waveguides in quite a range, speaking in terms of dimensions. So you can, similar to glass fibers, you can have multi-mode waveguides that are hundreds of micrometer big. But of course, we also do single mode waveguides, which are essentially what we're using in this chip packaging platform. And those waveguides are typically around 2 to 5 micron. What is also very important is that these waveguides are actually polarization maintaining. You can think about it that due to this rectangular shape, in contrast to optical fiber, you have a predefined vertical and horizontal polarization axis. And this is a really nice feature because some advanced telecommunication switching techniques, WDM, for example, they also rely partially on having these 2 polarization split. One thing that was discussed a bit before was already the mode field and connections to other technologies. This is a really nice thing here that we can basically change the geometry of these waveguides. We can create tapers in plane. We can also adjust the material, so the refractive index difference of the core and the cladding. And by that, we can change the mode field diameter more or less between 4 and 10 micrometer, which is really what you want if you want to couple to a PIC on the one hand, where there is a very small mode field diameter, and to a fiber or fiber array on the other hand, which standard optical fibers are in the range of 10 micron. This also relates then, of course, to the alignment tolerances. So if you want to couple to a fiber optic part, this is typically around 1 micron. And if you want to couple to a PIC, you need probably sub-micron alignment precision. Now, as mentioned, this optical layer, this is our core know-how of vario-optics. But as mentioned, what really adds on to this is that we have access to this PCB technology. And so here you see 2 technologies that we are developing and using. The idea is to combine this optical layer with electrical layers. You can do this on the left hand here by really sandwiching the optical layer between 2 boards. So you would basically have 2 electrical boards fabricated, and then you laminate the optical layer into the middle. This has certain advantages. It's very well protected from the environment. But of course, if you want to couple a PIC on top of such a board, then you need also optical access to this optical layer. That's why for these applications, we can structure and manufacture the waveguides on top of the board. Here you see a zoom in view. You see these stripes. These are actually the cores of the polymer waveguides. And this optical layer is here patterned on top of a highly planar PCB. And this is really necessary. You see it here in these pictures and in the sketch on the lower right. It's really necessary, for example, to enable then flip chip bonding, where you need a direct contact, of course, of your chip to the board. Just a quick word also regarding robustness of these boards. Since we are using standard PCB processes and manufacturing tools, these boards, including the optical layers, typically undergo the standard testing and requirements that you also have in the electrical boards. That means, for example, Telcordia tests, so longer, a few thousand hours at elevated temperatures. Also temperature cycling from -50 to 100. This is something we recently validated in our ESA technology validation. And this is also quite interesting. If you assemble such a board and place the components on, these boards, they also need to undergo reflow soldering. So that means 260 degrees. And we also do this with our optical layer integrated in the middle. Right, so now coming to PICs and coupling to these PICs, there are various schemes and ways to do this. Maybe first of all, here on the left, you can actually take a very simple die. Let's say if you have just a laser die or a photo die, photodiode, you can directly butt couple them to the optical layer. We also have means to vertically outcouple the light from our waveguides by using small mirrors. And speaking of PICs, there are two ways that we are mostly using. One is, again, sort of standard butt coupling, so really bringing into direct contact your PIC to the facets of the polymer waveguides. And the other one is this adiabatic coupling scheme that Sander mentioned before, and I'll have a slide on this later on. So I want to show two examples that use these two schemes. First, I didn't want to show this one actually, but I brought it up because we've talked about this before, about integrating micro-optical elements into PICs, or for using them for coupling into PICs. And this is a project, still ongoing project, Horizon 2020 funded, where our task is basically to develop a board. We're using a glass substrate in this case, which can be metallized to get access electrically to the PIC, and which also contains these polymer waveguides on top. These polymer waveguides can not only be used to couple into the PIC, but they can actually also have precise mechanical features. For example, they can have a sort of a step in the polymer, which means that you can basically use passive alignment in Z direction, and you don't only need to align X and Y of the PIC. Here you see a picture, so it's an indium phosphide chip in this case. And yeah, speaking of micro-optical elements, the role here of this board is also to use these mechanical features to assemble micro-optics onto such a board. You can, for example, put on a green lens or a cylindrical lens using these mechanical features. The second example that I want to quickly show is another Horizon 2020 project that we were involved in, ICT Streams. This project basically focused on developing several technologies from the PICs to the packaging part for something that we nowadays call co-packaged optics. We've heard this before. So the whole idea is that you have several photonic chips on one board, very close to each other, and you basically want to have optical communication between these chips. So this is exactly the scheme that this ICT Streams project had in mind and had as a goal. And so what I will show you now is basically one part of this. So it's a subboard basically of one chip that includes this electrical and optical layer. And I'm now saying this is sort of a subboard, but nowadays some people also think along the direction of having everything pluggable. So there's of course also pluggable optics, which has some benefits. So you could also see this as an individual module, similar to what Sander explained in the previous talk, that you can plug together. So this is how this board looks. This is the board from the very beginning. Again, you don't actually see these waveguides, only if you zoom in and if you know that they're there. But trust me, there is this optical layer. In this case, we're using this adiabatic coupling scheme, which really means that you bring to direct contact not only the electrical pads of the PIC to the board, but also you need to have access to the silicon waveguides of the PIC. And by bringing into direct contact the silicon waveguides with the polymer waveguides over a certain length, the optical mode will transfer from the PIC to the polymer and vice versa. This works very well, both in terms of loss and especially in assembly tolerance. The key here is that you sort of only need to be in contact with the polymer waveguide, but you don't necessarily need to be centered on the polymer waveguide. And now you can imagine if your polymer waveguide is around 4 or 5 micron wide, this is basically the range within which you want to place your PIC. And this strongly extends the assembly tolerance to around plus minus 2 micron in comparison to edge coupling, where we have around maybe 0.5, 0.7 micron. So here you see the fully assembled device in the lower middle. case, this is flip chip bonded to allow for this adiabatic coupling. And in this project, of course, the aim was to demonstrate higher data rates, in this case, 50 gigs over 8 channels at a very low power consumption. But this, of course, relates a lot to the silicon photonics chip that was used here. Okay, so with this, I'm done. I hope I could explain you the concept of these electro-optic circuit boards. Maybe as a short teaser and outlook, I also want to mention that, as some speakers pointed out before, we're also working a lot towards standardization. So our technology, we also have a broad portfolio of devices and designs, and the idea is to have PDKs available that can be integrated in the workflow of other PIC technologies. And on the other hand, of course, also with the electrical side. So this is a big part of what we're doing to really enable a seamless workflow for both PIC designers, but also for electrical PCB designers. Okay, so that was it from my side. Thanks a lot for your attention. Feel free to ask any question